Hello APChem students, this is Chapter 3, Stoichiometry, the Zumdahl 10th edition, pages 68 through 112. As you know, stoichiometry can be done from many different starting points. We can start from the mass of a solid and change it to moles and do the mole ratio and find the grams of the unknown, or we can start with the liters of a gas and use PivNerd or 22.4 liters at STP to change to moles, or we can even do it with a solution with molarity and change molarity to moles using molarity times liters. So there's lots of different approaches to finding moles and then changing from moles back to different units. However, the mole-to-mole ratio always stands out as a very important step in the stoichiometry. So keep in mind the ECMS approach that we learned in Chem 1. When it comes to mass, the idea of changing grams to moles starts with the idea of counting by weighing. Dr. Zumdahl in the book does a pretty good job on page 69 to 70 talking about weighing jelly beans in a candy store as a way of counting out the jelly beans. When you don't have the opportunity to count the items, you'll want to find the mass or the average mass of just one item and then use that average mass to find the mass of many of the items. So the idea is if a jelly bean has an average mass of 5 grams, then 5 kilograms would be 1,000 jelly beans. In the same way, if one atom of carbon weighs on average 12.01 atomic mass units, then a mole of carbon atoms would weigh 12.01 grams. We find these average masses because, of course, elements have isotopes. So we can't just assume the mass of one atom. We have to do the mass of an average of a set of atoms. As long as there are many, the average is a good way of finding the number and the mass of a certain number of atoms. We find the average mass by using data from a mass spectrometer. We have the diagram here of a mass spectrometer, and the mass spectrometer excites the atoms by knocking electrons off of them. Once they're negatively charged, they're accelerated by charged positive plates. These charged positive plates have holes or slits in them that allow those atoms to move through those charged positive plates, and once they get through 2 of those plates with their positions aligned, they'll be very much in a straight line. And so then once they hit the magnetic field, they're deflected. The lightest ions are deflected the most, and the heaviest are deflected the least. And so the detector can not only measure their mass by where they strike on the detector, but can also measure their relative abundance by the strength of the signal. Once you have the percent abundance, you can multiply the percent abundance in decimal form by the mass of that isotope and do that for each of the isotopes and then add up the total, and you've got the average mass of an element. This particular element here would be boron, because it has an average mass somewhere between 10 and 11, but we can tell because the boron 11 isotope is more abundant that we're going to have an average mass that's closer to 11 than 10, which seems to match for boron because it has a average mass of 10.8. Once we have the average mass of an atom, we simply need to change that from atomic mass units to grams, and we've got the average mass of a mole of atoms. The mole is defined as the number of atoms equal to exactly 12 grams of carbon-12 atoms. But of course it doesn't have to be carbon, it can be for any particular element. A mole of atoms will weigh what the periodic table says it weighs in grams. A carbon-12 atom weighs exactly 12 atomic mass units. which is the mass on the periodic table. Of course, we average carbon-12 with its other isotopes to get the average that's on the periodic table. The number of atoms in a mole, we call it Avogadro's number, and if we need to convert to atoms, we use 6.022 times 10 to the 23rd atoms in a mole. To convert a mole of a substance to particles means that you're using 6.022 times 10 to the 23rd times the number of moles to get the number of particles. Interesting connection here is that Avogadro's number is actually the number of atomic mass units in a gram, which is why it works out that the mass of one atom in atomic mass units equals the mass of a mole of atoms in grams. So you might think about that and see if you see why that works in that particular way. Bottom right here we have 3 different examples of aluminum, copper, and carbon, and we have the same number of atoms in each of these cubes, and as you can see, they're approximately the size that would fit in the palm of your hand. A quarter is shown there for reference. The copper may weigh the most. The aluminum might have the most volume, but they all have 6.022 times 10 to the 23rd atoms. Molar mass is the mass in grams of a mole of atoms if it's an element, or a mole of a compound if it's a molecule or an ionic compound. Masses for moles of compounds are simply found by totaling up the mass of the moles of atoms that make up the compound. So, for instance, if you have sodium chloride, you would add a sodium plus a chlorine. The mass of a mole of sodium plus the mass of a mole of chlorine to get the mass of a mole of NaCl. If you have something that has subscripts, you have to multiply by those subscripts. So as we go along through this lesson, make sure you're practicing with the examples in the book. Stoichiometry is sort of used as an example of problem solving in AP chemistry. Our conceptual problem solving technique, where we try to learn how to solve problems, is very, very, very important to first make sure you read the problem carefully, realize what the problem is asking for, and are able to identify what the problem is giving you as information. So once you have the information given and you know for sure where you're going with the final answer, it's often fairly obvious how to get from step 1 to the end. However, if it does need to be kind of mapped out, then you simply map out where you can go in step 1, where that can then take you in step 2, and so forth until you do get to the target where you're headed. So step 2, asking where do we start? What do we know? What relationships can we apply to what we know to get to where we want to go? We try things. We're not afraid to try things in chemistry. Chemists try. If you run into a dead end, you back up and you see if you can go a different path and get to where you want to go. But you just keep plugging until you are able to figure out how to get from the information in the problem to the final answer. I'll just interject this. Sometimes the information to solve the problem may not be given in the problem, but maybe somewhere in the textbook, like looking up a molar mass or looking up a particular value in a chart or table in the reading, and then once you have that number, you have the missing piece to solve the problem. Now, don't forget, once you've solved the problem, to go back and ask yourself, does the answer make sense? Do a reality check. Keep in mind that we do learn some algorithms. We do learn some approaches to solving problems, but make sure you're not only learning those algorithms, but you're learning why those algorithms take you from point A to point B, because AP is going to try to ask you questions that simply following the algorithm from beginning to end won't necessarily get you the final answer. They may take you off on a tangent and take you another direction. So just be aware that you need to not only know some algorithms and know some approaches, but you're also able to adapt to new problems when you run into them. One typical problem that we have in chemistry is the percent composition problems. These are typically percent composition by mass. The percent composition by mass is calculated using the formula that the percent by mass of an element in a compound is the mass of the element in 1 mole of a compound divided by the molar mass of the entire compound. So it's the part of the compound that is the mass of the element divided by the whole of the compound and the entire molar mass of the compound. Once you have that ratio calculated out as a decimal by dividing, multiply that by 100 and you've changed it to a percent. Percents can be converted to formulas using the approach of finding the percent and changing the percent to grams, changing grams to moles, and then finding the mole ratio of the moles by dividing by the smallest and then simplifying those moles to whole numbers by multiplying until you get all whole numbers for all of your elements. That's the typical approach to solving for the empirical formula of a compound. One way that can be done is if you have, say, a hydrocarbon, something with just hydrogen and carbon, you could burn it in a furnace with oxygen, take the exhaust from that, and use a water absorbent chemical to extract the water from the exhaust, and then use a carbon dioxide absorber to extract the carbon dioxide, weigh the amount of water, weigh the amount of carbon dioxide, and then change the water to hydrogen, or convert from water to hydrogen, convert from carbon dioxide to carbon, and then figure out your percent carbon and your percent hydrogen in the hydrocarbon. We'll work examples of these in class, but you can also see examples worked in the textbook 1310 through 1312. Of course, for stoichiometry, we're going to need to know that we can balance chemical equations in order to find the mole ratios. Chemical changes involve reorganizing atoms, very much like taking a Lego creation apart and putting it back together to make some different Lego creation. We're trying to turn reactants into products. We want to make sure all the atoms are accounted for. In other words, we balance the equation. If we do need to know if there are solid, liquids, or gases or aqueous chemicals involved, we can add those symbols to show that. The balanced chemical equation can be represented as words, as pictures of models of atoms and molecules, or as chemical symbols such as CH4 plus 2O2 yields CO2 plus 2 waters, or it can be represented as a mole ratio of 1 mole of methane to 2 moles of oxygen make 1 mole of carbon dioxide and 2 moles of water. We can also represent it as number of molecules or grams. Of course, when you represent it as grams, you find out that 16 plus 64 on the left makes 44 plus 36 on the right, or 80 grams equals 80 grams. Law of conservation of mass. Section 3.9 is about how to balance chemical equations. Typically, we balance by adding coefficients in front of chemical formulas. We do not want to change our subscripts because the subscripts are there because that is the chemical formula of the chemical. Most equations that we balance are balanced by inspection. We just keep going back and forth from left to right, adding numbers in front until we get the smallest whole number ratio that balances the equation. Stoichiometry is typically done in an ECMS approach. We balance the equation, so that's the E. Convert the known mass of the reactant or product to moles, that's the C. Use the balanced equation to set up the appropriate mole ratios, and use those mole ratios to calculate the moles of the desired reactant or product. So that's the M. And then the S step is when we solve for the units that they ask for in the answer, typically changing moles back to grams. Below we see a stoichiometry problem where we work from the grams of aluminum to find the grams of aluminum oxide that would form with excess oxygen. In the first step, we take our 6.5 grams of aluminum, divide by 26.98 to get the moles of aluminum. Then we multiply by a 2 to 4 ratio of moles of aluminum oxide to moles of aluminum. Then we multiply by 101.96 grams, which is the molar mass of aluminum oxide over 1 mole. And units all cancel out, and we get 12.3 grams of aluminum oxide. So that would be a typical ECMS stoichiometry problem. Notice instead of stopping at the end of each step, this particular problem kind of strings them all together. The next hardest kind of problem to deal with in stoichiometry is the concept of limiting reactants. If we take a food example, a sandwich needs 2 slices of bread and 3 slices of meat and 1 slice of cheese, and you happen to have in your possession 8 slices of bread, 9 slices of meat, and 5 slices of cheese, then obviously you're going to run out of meat first. You only have enough meat being your limiting reactant, to make 3 sandwiches, even though you have enough bread to make 4 and enough cheese to make 5. You only have enough meat to make 3. So determining which reactant is going to make the fewest amount of products is how we determine which one is our limiting reactant. Once we've determined our limiting reactant, everything in the problem can be based on the limiting reactant, because, for example, in this sandwich problem, the number of sandwiches depends on the number of slices of meat. How many slices of bread you make depends on the number of slices of meat. How many slices of cheese get used depends on the number of slices of meat. Everything that is used and formed in a chemical equation is based on the limiting reactant, because that is the one that rules all the others in terms of how much of each one is used and made.